Dear students, we start learning 15 questions as a starting point for our CET class. That is 15 questions from electric charges and field, the first chapter of second year. Now the question is seen in this paper. Let me read the question first. When 10 raised to 19 electrons are removed from a neutral metal plate, the electric charge on it is, observe, it contains number of electrons removed. Removed means we know when electrons are removed, substance gets a positively charged, because we know shortage of electrons actually makes the metal positive. Therefore, now using the quantization of charge, we can write Q equals N into E, where E is charge on electron, N is number of electrons, Q is the charge. Therefore, N is given to be 10 raised to 19 into charge on electron, as we know, 1.6 10 raised to minus 19 coulomb. Therefore, 10 raised to minus 19 and 10 raised to plus 19 goes, and we have 1.6 coulomb. As metal is positively charged, as it is having shortage of electrons after removal of electrons, the option 2 is right. That is, option 2 is right. Now, going for the question 2. Here, let us read the question first. A point charge A of plus 4 microcoulomb, another point charge B of minus 1 microcoulomb are placed in air distance 1 meter apart. Then the distance of the point on the line joining the charges and from the charge B, where the resultant electric field is 0, is in meters. Say here they are asking us to calculate the null point, because electric field intensity 0 means it is called as null point. Also observe, one positive charge, one negative charge are given. So when unlike charges are given, the null point lies outside the charges, that is on line joining the charges but outside the charges. Let me write the figure first. Let us take A here and this is B. At B I have a charge QB, what I call as minus 1 microcoulomb. At A I have QA, what is 4 microcoulomb. Now the null point lies at a distance x from B. I took C near to B because A is larger. Therefore, the null point will be lying nearer to the weaker charge. Therefore, B. Nearer to B, I have charge C. Now at C, I have two field intensity vectors. One, say, electric field due to charge A. What is repulsion there? And I can write it as ECA, electric field intensity at C to charge at A. In the same manner, due to minus 1 microcoulomb, electric field intensity at C is attractive towards the B. Therefore, I can write this as ECB. Now, for null point, ECA must be equal to ECB. But we know now the distance between A to C is 1 plus x, because they have given this distance as 1 meter, A to B. Now, we write the expression for field intensity 1 by 4 pi epsilon naught. CCA means charge at A to be written, divided by distance, as it is in the notation CA, I must write AC square. Is equal to ECB 1 by 4 pi epsilon naught, charge at B to be written divided by the distance as it is given by CB, it is CB square I have to write. Now cancelling all those things and substituting. I hope all of you are getting that. QA, I write 4 micro. AC, I write 1 plus x whole square is equal to QB 1 micro. Observe, I am not taking the sign of the charge because sign of the charge is taken when we write the vector equation. Now we are transferred the vector equation into scalar, so I am not writing the sign of the charge there. Now CB is x square, so cancelling mu there, I can finally simply write x by 1 plus x the whole square equals 1 by 4. Taking square root, x by 1 plus x equals 1 by 2, or simply I can write 2x equals 1 plus x, or 2x minus x equals 1, or x equals 1 meter. Therefore, the distance of null point from point B is at 1 meter. The option 4 is right. Option 4 is right. I hope you are getting it. Here we are using the concept that null point is the one where net field intensity is 0. Now we go over to third question. We read it. A charge Q is placed at center of line joining two equal charges Q. The system of three charges will be in equilibrium if Q is equal to. Now it is a question of equilibrium. As equilibrium is given and it is a system of three charges, two capital Qs and one small q, the net force on each charge should be 0. That is the important concept we want to use. We write the figure here. I write charge Q at A and another charge Q at B. I join them together. Now the distance between them, I take it as R. I mark this midpoint as C. Therefore, the distance between C and B is R by 2, A and C is also R by 2. Now, we write down the force on A due to charge at B. As both charges at A and B are positive, there is a repulsive force on A due to B or B on due to A. But I write only on one charge A. I write it as FAB. FAB. That is force on A due to charge at B. It is also a vector. Now, to make the system to attain the equilibrium, this FAB should be cancelled by the charge going to be placed at C. That means this charge Q, what we place at C, is going to create a force opposite to FAB and of same magnitude. Therefore, to create an opposite force to FAB, it tells us Q should be negative. Therefore, I write Q is negative. The sign of Q is negative. Now, if I write the force due to Q now, the charge at C, I can write like this. On charge A, FAC. Now, as the system of charges to be in equilibrium, FAB should be equal to FAC in magnitude. Therefore, I write FAB equal to FAC. I am taking only magnitude because they are equal and opposite. Should be equal and opposite. Therefore, Now we write the expressions for FAB. 1 by 4 pi epsilon naught. AB stands for charge on A and charge on B. That is Q into Q. AB, the distance, R square, is equal to FAC 1 by 4 pi epsilon naught. A, charge on A is Q. Charge at C is small q by the distance AC is R by 2 the whole square. Now cancelling all the things what we can cancel here. R square also goes there. I got Q equals 4Q. Therefore, the Q, the charge to be placed at C, must be equal to Q by 4. As we have written Q as negative and the magnitude is Q by 4, our option 4 is right. That is Q with the sign minus Q by 4. Option 4 is right. So I hope you understood here. Now with this, we proceed on to the fourth question. Before that, once again, observe, we have taken the force to be 0 and only one charge here. But only once we calculate this, that is valid for C, that is valid for B also. Therefore, the whole system of 3 charges will be in equilibrium. And as I am saying you, along with the concepts, it is taking some time. If you are well versed after practicing all these questions in the concepts, you can do it very quickly within half a minute or so. Now we will proceed on to fourth question like this. Let us read it. Now, I hope all of you are getting it. Now we read. Two equal negative charges minus Q are fixed at 0, A and 0, minus A on y-axis. Observe, they have given the points on y-axis. And then, now we write the figure for that if you want. The figure goes like this. Let this be our y-axis. This is our x-axis. This is our y-axis. Now they have given charge minus Q at 2 points. One we call it as A, coordinate 0, minus A, and B 0, plus A there, 0, minus A here. This is our B. That is the figure what we can write for the first sentence. Going for the second sentence, a positive charge Q is released from rest at a point 2A, 0. Observe, it is on the x-axis at a distance 2A from the origin. O. It is 2A, 0. Here we have charge capital Q. At A we have charge minus Q. At B also we have minus charge Q. Now looking at this configuration, charge at A minus Q, charge at B minus Q, both of them will attract the charge. They attract the charge on the lines joining them. We write the lines like this. So they act force on capital Q in these directions as the force is attractive. I call this force as F, say, and this also as F, due to charge at A and due to charge at B. But observe, as Q is symmetric regarding A and B, FA must be equal to FB, and they create, both of them create a resultant of them along the x-axis as like this, but towards the origin. That means the charge is capital Q is acted by net force F towards the origin. That makes charge to accelerate towards the origin. But once it comes to the origin, due to its more energy, kinetic energy, it will pass on to the other side. But as it passes on to the other side, similar on to this side, on the other side, a force starts acting towards the origin, and after some time passing on to the other side, it stops, that capital Q stops and starts turning back. Therefore, the charge capital Q starts oscillating over the origin. But the problem is now whether this charge going to perform SHM, the simple harmonic, or not. But observe, as we can see from the above discussion, this charge is continuously oscillating. But we cannot say it is SHM because electrostatic forces are inverse square law forces, and F, net F, may also depend on the inverse square of the distance. Therefore, that will not be satisfied by the SHM equation F proportional to minus x. Therefore, the charge oscillates, but not SHM. Therefore, the option 2 is right. Therefore, our option 2 is correct. So here observe, the two forces are attractive. They pull the charge capital Q towards the origin. That means there is a net force towards the origin. On passing on to the negative side of the axis, that net force again changes on towards the origin. Only that makes the charge oscillating. But we cannot say it, as the force is continuously variable as the Q moves towards origin, and it cannot directly depend on x. Therefore, it is not SHM. We got all these things. Now, we proceed on to the fifth question. Say, we read. Here also, it depends on a peculiar, concept of combining the drops of mercury or any drops of liquid. We read the problem. 64 small drops of mercury, each of radius r and charge q, coalesce to form a big drop. The ratio of the surface density of the charge of the each small drop with that of big drop is, we are asked to calculate the ratio. Now we do one thing. We know when we have n drops of liquid combine to form, coalesce or combine to form a big drop. The radius, if each small drop is of radius r and each big drop is of radius r, the radius is having a relation capital R equals n to the power of 1 by 3 into small r. By using volume of all n drops is equal to volume of big drop, we can arrive at this. Now, we are asked to calculate the surface charge density ratio. For that, we also know the additive property of the charge. When we combine n drops, if each drop is of charge q, when we combine n drops, the net charge should be nq, and that should be the charge capital Q on the big drop. Now we know the radius, we know the total charge on the big drop. We write expressions for surface density of charge, on small drop, that is sigma S is equal to charge by surface area 4 pi r square. On big drop, sigma B capital Q 4 pi r square if we substitute n cube and 4 pi n to the power of 1 by 3 r whole square, we get sigma b as n to the power of 1 by 3 sigma s. Therefore, the required ratio, sigma s to sigma b equals n to the power of 1 by 3. N to the power of 1 by 3. Therefore, that is n to the power of minus 1 by 3. Sigma s to sigma are 1 by n to the power of 1 by 3. 1 by n is 64 drops. Therefore, to the power of 1 by 3. Therefore, sigma s to sigma b is n. 4 cube is 64. 1 by 3. So 1 is to 4. The option 4 is right. Here, you need not do all these things when you actually face the competitive examination. You can use a shortcut directly. Sigma s to sigma b is just directly n to the power of 1 by 3. You can straight away use sigma b by sigma s n to the power of 1 by 3. This is the shortcut what you can remember. I write here a short formula or a shortcut formula. Sigma b by sigma s is n to the power of 1 by 3. This is the formula what we can use. Now, I hope you got the answer now. I hope you have understood the things. Now we start with the next question. Say that is question number 6 to be solved. Observe, we read. The inward flux and outward electric flux from a closed surface are respectively 8 into 10 raised to 3 and 4 into 10 raised to 3 units. Then the net charge inside the closed surface. Observe, this is a problem on Gauss law. They have given inward flux. Inward flux. I write phi I as 8 into 10 raised to 3 and outward phi O 4 into 10 raised to 3. We know from Gauss law net outward flux is equal to 1 by epsilon naught charge enclosed. But observe now, net outward flux means phi O minus phi I equals 1 by epsilon naught Q. Phi O, I write 4 into 10 raised to 3 minus 8 into 10 raised to 3 whole into epsilon naught is Q. Therefore, our final answer, charge enclosed is minus 4 into 10 raised to 3 epsilon naught. Therefore, option 2 is right. Epsilon naught coulomb. Therefore, option 2 is right. So, option 2 is right. Here we simply use Gauss law. In the exam, as you are doing it mentally, or you can do it on the mind, you can simply go for within, say, quarter of the minute, within 15 seconds, you can simply write the answer because you know the outward flux, you know the inward flux, subtract in the mind and multiply it with epsilon. You will get the answer. So option 2 is right now. Now after 6th question, we go on to 7th. 7th is just a logical type and also it depends on the concept what we know. We read, an uncharged sphere of metal is placed inside a charged parallel plate capacitor. The lines of force will look like. Observe, in the four figures given, we are given metal plates and a sphere shown. But we know lines of force properties, lines of force are always normal to the conducting surface. Therefore, compared to all the four figures, in the first figure only, all the lines of force, the 3 on top and 3 on bottom, excluding the edge line of forces, these are excluded, and these 3 and these 3 seems to be exactly on the normal to the sphere. Therefore, the option 1 is correct. Now, going over to 8th question. So, before going over to 8th, let me repeat 7th. In the 7th, what the idea which we use, the lines of force are always normal to the conducting surface. And also here is one small glitch. They have given the edges are perfectly straight field lines. It cannot be. This is possible only when we think of the large metal plates. Therefore, excluding those things, our answer is right now. The option 1. Now going for the 8th. This is also an easy one. We just think over it. If possible, we write. If we require, we write a figure. A free unit positive charge is kept at a distance r along the equatorial line from two equal like charges plus q1 and plus q2. The unit positive charge, let me write the figure here itself. It's a simple figure. I write q1 and q2 here. This is the equatorial line. On the equatorial line, I must place a unit positive charge plus 1. Now observe, this plus 1 at P is repelled by charge q1 at A along the line joining the charges like this. It is going this way. And in the same manner, the plus 1 unit positive charge is repelled in this way by the charge at B. So, both the forces on unit positive charge are acting like this. Their net force will be in the upward direction as I marked in this red. Therefore, that charge, unit positive charge, starts moving in the upward direction on this equatorial line. Let us now learn what are the options there. Does not experience the force is not possible. Moves vertically upwards along the equatorial line. So this is the answer what we got there. So option 2 is right. This is the question number 8. Here a simple logic in these two, 7 and 8. Simple logic will help us to solve these problems. In this type of problems, we must save the time. Say, we need not take 1 minute for all the questions in our CET where 1 minute is allotted for each question. In this type of questions, we have to save time by answering them within 15 seconds or so, and then so that we can get more time for answering little bit lengthier questions now. Now we go for the next question number 9 like this. We read it. The electrostatic force between two charges of 10 microcoulomb and 20 microcoulomb at a distance 2 meters to be halved. This can be affected. Observe here, we are given two charges, 10 microcoulomb and 20 microcoulomb at distance 2 meters is to be halved. First to simplify our calculation, first we calculate the F1 when D equals 2 meters. F1 is K Q1 10 micro into 20 micro divided by distance square 2 square. Here, if we can calculate, this is 9 into 10 raised to 9. So, that is 10 into 20 into 10 raised to minus 12 divided by 4. That means 4 5s are. So, now what is the answer for this? We calculate. 4 5s are, first we complete the powers. 10, 1, 10 is there, 1, 9 is there. 10 to the power of 10, it happens, and minus 2 is, minus 12 is there. So I can simply write it as 10 to the power of 10 minus 12 is minus 2. And here have 9 left and 5 left, 45 only. 45 into 10 raised to minus 2 Newton. Now, we want to reduce this to, say, half. This can be affected. We have to reduce the force to be half. That is, our F2 should be F1 by 2. F1 by 2. Now, we have to see each option and we have to think of F1 by 2. That means that implies 50%. That means that implies 22.5 into 10 raised to minus 2 Newton when it happens. So we'll go for 1 by 1. One by one. Observe now. Say in the first case, reducing both charges by 50%. We do this. For option A, we try. F2 is 1 by 4 pi epsilon naught. 2 charges by 50% means 5 and 10 divided by distance 2 square, which amounts to be whole thing divided by 4, that is 22.5 10 raised to minus 2 by 4, which is not 50%. It is 25%. So option A is not possible. We go for option B. Reducing both charges and their separation each by 50%. We do that now. According to B, 1 by 4 pi epsilon naught. Reducing both charges by 50% means again 5 into 10 divided by separation also by 50%. That means 50% of 2 meter is 1 square. Now what we have is, say, if we calculate this, 9 into 10 raised to 9, I have to write minus 12 there, 9 into 10 raised to 9 into 5 into 10 into 10 raised to minus 12. What I can write now is, say, I can write 45 here and 10 raised to 10 minus 2, 45 minus 10 raised to minus 2. So this is same as F1, therefore B is also not possible. We go for C. By doubling one of the charges and doubling the separation between them, we try this. F2 according to C is 1 by 4 pi epsilon naught. Doubling one of the charges means 2 into 10 into 20 into 10 raised to minus 12 divided by doubling the separation. Doubling the separation means 2 into 2 whole square. This amounts to be, observe, compared to the first calculation, that is F1 calculation, we have the extra things only this much. 2 by 4 in the denominator, all other things are same, therefore it is 45 only. Therefore I can write 2, which amounts to be half of that, that is 22.5. Therefore F2 is 22.5. We got, which is 50% of F1. Therefore option C is right. The force is out Now force F2 is hard. I hope you got the calculation. But observe, as I told you in the previous two questions, if you save the time, for this type of things you can give some more time. But instead of doing this calculation, you could have done directly in the mind when we reduce the charge what happens. But to explain to you, I have written all these things. But you can do it by practice in a quick manner to get this. Now once I solve this, the right answer for this is C. Now we go for the 10th question. Say, 10th question, it's also direct knowledge based question. We read, identify the wrong statement in the following. Coulomb's law correctly describes the electric force that, first option, binds electrons and atoms in the nucleus, definitely, but it is again it should be in the atoms, not in the nucleus. Second option, that is a wrong thing. Second option, say in the first thing, binds the electrons and atoms of an atom to the nucleus, definitely right, because according to the Bose postulate, it is right. Second one, binds the protons and neutrons in the nucleus of an atom, it is wrong, because inside the protons and neutrons inside the nucleus are attracted or acted by nuclear forces, not by the electrostatic forces. Therefore, this is the wrong statement and option 2 is right. Say two more are like this. Binds atoms together with together to form molecules. Definitely it is possible either in covalent bond form or ionic bond form. In anywhere it is like that. Fourth one, binds atom and molecules to form the solid. That's also true. Therefore, to go for once again quickly, if first one is wrong, first one is correct because electrons are attracted by the protons inside the nucleus by electrostatic forces. Only second one is the wrong statement. That's all for the 10th question. We go for the 11th. The flux, electric flux for Gaussian surface A that encloses charged particles on the free space is given by 3 charges, and the answer, the figure they have given is printed on this side. Q1, Q2, Q3. Now we are asked to calculate the electric flux. So I directly write Gauss law. Phi equals 1 by epsilon naught times Q1 plus Q2 plus Q3. I substitute everything there. Q1, I substitute for also epsilon naught, 8.85. Now into 10 raised to minus 12. For Q1, I write, say, minus 14 nanocoulomb. Minus 14 into 10 raised to minus 9 plus. Going for next one, Q2, 78.85. 78.85, 10 raised to minus 9. And the last one, minus 56, 10 raised to minus 9. Now observe, looking at this itself, 56 and 14 both are of minus sign, which amounts to be 70 there. 70 with minus sign, 78 with plus sign. That means what we left on the numerator is simply 1 by 8.85, 10 raised to minus 12. Here 8.85, 10 raised to minus 9. Only that much is left. Therefore, if we cancel these things, we get 10 raised to 3. Now, we look into the options given there. Say 10 raised to 3, first option. Second option is also 10 raised to 3. But only thing, units are different. In the first, Newton meter square Coulomb inverse. In the second, Coulomb Newton inverse meter to the power of minus 2. But the flux unit is Newton meter square Coulomb inverse. The option is 1. Option is 1. Therefore, option 1 is correct for this Option 1 is correct for this. Now we go for the 12th question straight away. It requires some calculation. We'll read it. Two identical metal spheres with charges 2q and minus q are separated by a distance. Force between them is F. They are connected by a conducting wire and then removed. Force between them is now. In fact, observe, in the beginning, the force is F. Once we connect them together, they have to acquire same potential. It's a very important tool. Whenever we connect two conductors, one charged, other uncharged, both the charged, like that, finally they acquire same potential. We have to use that logic here. And also it is given two identical spheres. That means their radius are same. Now let me write initial force before connecting. Initial force before connecting them is F. What I can write as the K constant, 2q minus q, say not minus is not required, divided by distance I take d square, but I call it as Fi. Now after connecting them together, they acquire the same potential. So I write potential of first sphere V1 should be equal to potential of second sphere. That means as radius is same and charge additive property tells us 2q minus q will result in total charge q only, we can simply say charge on each sphere as q by 2 by logic itself. If you want, you can prove that from this. We can go for it. Say we can write q1 on 1, q2 on 2. So potential will give us k q1 by r1 r, k q2 by r. Observe, I am taking r same because they are identical spheres. So it is given q1 equals q2. That means total q equals q1 plus q2. That is 2q1 as q1 equals q2. Therefore, q1 as I have shown you here, therefore q1 equals q by 2. Similarly, q2 is also q by 2. Therefore, the new force or final force F equals Ff equals K. Now the charges are q by 2 into q by 2 divided by same distance d square. So I can write it as 4k q square by d square, what is nothing but Ff is can be written as kq square by d square. Here Fi is 2qq square by d square. Therefore, I can write it as Ff as Fi by 2 divided by 4. That is Fi by 8, or Fi is nothing but F by 8. Therefore, option 2 is right. Option 2 is right. So this is the 12th question what we learnt. Observe here, very important concept what we used. It comes to your hand whenever you think of two conductors are joined together. In any case of in any metallic conductors charge with charges case. So this is very important. V1 equals V2, and in particular if they are of identical, that is radius, then charges also get equally divided. So this is very important point to be actually